Stokes equations and proof. The Navier-Stokes existence and smoothness problem concerns the mathematical properties of solutions to the Navier-Stokes equations, a system of partial differential equations that describe the motion of a fluid in space. Solutions to the Navier-Stokes equations are used in many practical applications. However, theoretical understanding of the solutions to these equations is incomplete. In particular, solutions of the Navier-Stokes equations often include turbulence, which remains one of the greatest unsolved problems in physics, despite its immense importance in science and engineering. Even more basic properties of the solutions to Navier-Stokes have never been proved. For the three-dimensional system of equations and given some initial conditions, mathematicians have not yet proved that smooth solutions always exist, or that if they do not exist, they have bounded energy. This is called the Navier-Stokes existence and smoothness problem. Since understanding the Navier-Stokes equations is considered to be the first step to understanding the elusive phenomenon of turbulence, the Clay Mathematics Institute in May 2000 made this problem one of its 7 Millennium Prize problems in mathematics. Prove or give a counterexample of the following statement. In three space dimensions and time, given an initial velocity field, there exists a vector velocity and a scalar pressure field, which are both smooth and globally defined, that solve the Navier-Stokes equations. So proof. All functions from 3D to 3D have analytic answers, so we should prove it works even on micro world. So we need definition of particle first. Object is a particle if and only if it has duality, and duality is always possible when there exists maximum entanglement entropy, which is always satisfied with enough time. And in this equation, particle is an object which first has duality. So particle in particle doesn't count, and defined particle should have fractal structure because the structure below 3D can be fractal arrays. And hologram theory says all information is recorded in 2 dimensions when all information has entanglement to be maximum. There is a network near the surface of CFT with the shape of string and wave, and the shape of network has fractal structure which has dimension between 2 and 3. So it is obvious that an object with a maximum entanglement entropy there always exists fractal structure related to network, and within proper strategy, the shape can be altered to what you want because we can define the bursts inside. Then you can solve this equation. First, the movement of finite particle always satisfies N's equation because it is defined in 3D vector field. And you define the particle should follow fractal structure, so the movement inside particle should follow N's equation. So we proved N's equation. Entanglement entropy is a good tool to measure how much two regions are entangled. The maximum entropy is limited, which is the value for duality to exist. And I'll show that what is entanglement entropy. Consider a quantum system that is divided into A and B, two parts such that the full Hilbert space can be represented as the tensor product of the Hilbert spaces of A and B. A typical wave function of this system is psi. In which A and B in the state psi are entangled, since psi cannot be written as a simple product of those A and B. Entanglement entropy is a measure to quantify how much A and B are entangled. Define the reduced density matrix of A by tracing of all B state is in psi, then entanglement entropy is defined as this. From the definition, an obvious corollary is this. Indeed, for any pure state psi, we can always write it as this. By geometric decomposition of psi into some complete set of S A and B, it follows that SA is SB. For AB composite system in a mixed state. In general, we have SS, not SB. In such a case, entanglement entropy typically contains classical statistical correlation of the mixed state in addition to quantum field correlations. Here are some examples. A two-spin system. You can have a state that is not entangled. However, the state is entangled. For this state, the reduced density matrix for A is this shows entanglement entropy is this. We see as entanglement A has period of this. The minima are SA is 0 when theta is n pi over 2 and maxima are SA is log 2 when theta is n pi over 2 plus pi over 4 where n is integer. A maxima of state psi is most integer. We list some important properties of entanglement entropy as follows. Suppose A, B, C are three parts of the system without any intersection between any two of them. We have subadditivity and strong subadditivity. Entanglement entropy plays an important role in quantum information and quantum computation as it provides quantitative measure of quantum correlations that are not present classically. Entanglement entropy in many-body systems. Consider a system AB if Hamiltonian is H equals HA plus HB, then the ground state is unentangled. Moreover, starting with a general unentangled state, the system will remain unentangled. If we add coupling between A and B, H is HA plus HB plus HAB, then the ground state is generally entangled. Thirdly, starting with an initial unentangled state, entanglement will be generated during time evolution. In all realistic condensed matter systems and quantum field theories, HAB is local. Heisenberg model and 5/4 powers quantum field theory. Locality implies that the interaction only happens near the interface of A and B. So HAB only inverts degree of freedom near DA and DB. This has important implications. Locality of interactions. One finds in general in the ground state for a local Hamiltonian, entanglement entropy is given by this, where epsilon is the lattice spacing for CM system or short distance cutoff for quantum field theory, which characterizes the geometric width of interface. This formula shows that entanglement entropy between A and B is dominated by short-range entanglement near DA, where HAB is supported, while 16 appears to be universal, sharp is not. Depending on short-distance physics of specific systems, for the subleading order terms, the excitement of last decade on entanglement entropy shows that they come from large-range entanglement and can provide important characterization of a system. Characterize topological order 2 plus 1 dimension in typical gap systems. Ground state contains only short-range correlations. In topological order systems, ground state contains long-range correlation and not accessible via standard observables such as correlation functions of local operators. The entanglement entropy for such a system is this, where gamma is not zero is topological order, a constant independent of shape and size of A. 2. Characterize the number of degree of freedom of a quantum field theory for a 1 plus 1 dimensional CFT. There's no leading contribution, and one finds this, where C is central charge and L is the length of A. We know C contains the information of number of degree of freedom of a 2-dimensional CFT via Cardi formula. For 2 plus 1 dimensional CFT, one finds this, where gamma, depending on the shape of A, can be used to characterize the number of degree of freedom. Similar results can be found in other dimensions. Holographic entanglement entropy. Suppose we have a CFT with a gravity dual. How can we calculate entanglement entropy on the gravity side? As shown in the picture below, we propose to find the minimal area surface of gamma which extends into the bulk with dA as boundary, and entanglement entropy is given by this. This formula was first guessed by Liu and these who were motivated by black hole entropy. Minimal area. There are some support for this formula. One, satisfy the strong subadditivity conditions. 2. Reproduce known results about entanglement entropy. 3. Give many new results that are sensible. While easy to define, entanglement entropy is very complicated to compute for a general many-body system. Even for a free quantum field theory, The computation is highly non-trivial and often numerical calculations are needed. RT provides a very simple way to compute entanglement entropy in a class of strongly interacting quantum field theory. Here are proofs of strong subjectivity. In figure 3a, we can classify this. And by definition of minimal surface, which implies this. In figure 3b, we also have this. And by definition of minimal surface, this, which implies this. Now we can apply this formula to 1 plus 1 dimensional CFT whose duality is 3 where the matrix is. We know each CFT is characterized by a central charge C, density of state, and the trace normally gives this where R is Ricci scalar for holographic CFT. The central charge is given by this. On the gravity side, like Wilson rule, we consider constant time slice where the matrix is assume the minimal surface is a function of xc. The differential length of the surface is this, consider right half is this, and extreming it lead to the random answer, the half circle with c0. Finally, we get entanglement entropy, where epsilon is the cutoff to regularize the divergence. Clearly, this result agrees with the calculation from CST. In finite temperature, we may discuss the connection to black hole entropy. Consider the CFT on the circle. We should recover black hole entropy if we take A to be the whole boundary space between by definition. Because by definition, as the thermal entropy, and in this case, the reduced density matrix is the same as the real density matrix of A. Indeed, graphically, the minimal surface is just black hole horizon and black hole entropy is recovered. Generally, if the minimal surface is always perpendicular to boundary, area law can be proved in edges in arbitrary dimensions. RT formula not only provides the simple way to calculate entanglement entropy, but more importantly, it implies some connection between space-time and geometrization of quantum entanglement, geometry, and quantum information. In the end, we may expect a unified paradigm.